Okay. This is homework 2, part B, cylindrical cup with R and height. T contains water at liquid level H. It is rotated at W, angular frequency. We are asked to derive the max angular frequency the cup can be rotated at without overflowing. I'll draw a picture. Here's our cup. Here's our liquid level. Here's our end liquid level. We know that there will be different diameters here to account for. So first we will find our pressure and solve for H, and then we will find diameter and solve omega. We know that the acceleration, the radial acceleration, is equal to omega squared times radius. So to start finding pressure, we know that the differential pressure with respect to radius is going to be equal to our radial acceleration of omega squared r times our density of the liquid. So we will move this to this side, and that will be dp equal to w squared r dr. Integrating both sides, we can obtain pressure as omega squared r squared over 2 times density. We also know that pressure is equal to rho GH, so we're going to set that equal to this pressure of omega squared r squared over 2 times density. So we can cancel these and divide both sides by G to obtain our H. So this is the height of the water for the angular rotation, angular frequency. Okay, so that was this initial step. Now to find our changing diameter, we know that we can multiply that by our area, the cross-sectional area, pi r squared, and that is equal to the cross-sectional area with respect to r. We can cancel these because they're constants, but we have to leave these because of our different integrations. So we plug in our h that we found for h in here, and that looks like the differential diameter, r squared, is equal to 2r omega squared r squared all over 2g. So this cancels, and then we can condense this and integrate. Like this. Forgot to bring that down. So integrating this here, as I said, we can do d r squared is equal to omega squared times r to the 4th divided by, oh, I rewrote that. That's not true. There we go, because I already canceled it. Divided by 4g. Now we can cancel because we've integrated, and we get diameter equal to omega squared r squared over 4g. We can set up an equation to find the total height, and that is equal to h naught minus our diameter plus our h. Yeah, okay. So then we know t is equal to W squared R squared over 2G minus our diameter that I just solved, omega squared R squared over 4G plus H. All right, so we can condense these, and that looks like this. Negative, apologies, plus H. So we're going to move this to the other side and then get rid of our negative, and that will look like H minus T equal to omega squared R squared over 2G. Using algebra, we can do it like this. And that gets rid of that, and then divide the whole thing by R squared, and that is what is equal to omega squared. Doing the last step, we find that omega is equal to H minus T times 2G, and then our R will just be R. And that is our equation to find the frequency that the cup can be rotated without overspilling past here. All right.